So welcome back. In power electronics, we are in lecture 6A where we are going to discuss on thyristors, its principles and characteristics. So the lecture that we are going to cover roadmap, let us see. So here we will be discussing the introduction to thyristors, what are its structure and operation, the characteristic of thyristors, in terms of the VI characteristic as well as the key parameters. We will be discussing the turn on and turn off methods and characteristics, the protection methods, what are the application, and compare the device with the other power semiconductor devices. Use the thyristor in series and the parallel mode, some advanced topic and what are the future trends. Then we will conclude the lecture. So let us begin with what is a thyristor. So thyristor is basically 4-layer, 3-terminal semiconductor device. So we were discussing the other semiconductor device like the bipolar junction transistor, the MOSFET and the IGBT. So we were discussing about the different semiconductor devices, and in these semiconductor devices topic, we will be now covering one of the important semiconductor, not device but a group of devices. The name is known as the thyristor. So it is basically 4-layer and 3-terminal. And the most famous device in this thyristor family is basically the SCR, which are known as the Silicon Controlled Rectifiers. So whenever we say the thyristor, the analogy is the SCR which we are talking about. So the historical context, if we see, SCRs or the thyristors were invented by General Electric in the year 1957. It was one of the revolutionary impact in the area of power electronics because it formed the foundation of modern industrial control. So with the invent of SCR, the industrial application in terms of high power, high current changes a lot. So it was considered to be one of the revolutionary discovery. Some of the key features which we are going to see in the lecture ahead, it has the high voltage capability up to 12 kilovolt and also the high current capability up to 6 kiloampere. Like other semiconductor devices, it is also unidirectional current flow and it has the latching behavior which is self-sustaining. We will discuss about the latching behavior in detail a little bit later. So if we talk about the critical property of this thyristor is that once this thyristor is triggered, it cannot be turned off by the gate control. So it requires certain current interruption techniques, which are known as thyristor commutation techniques. So the gate is basically used to on the thyristor, but if you need to off the thyristor, you will be requiring certain devices or external circuit, which are known as thyristor commutation techniques. In terms of the structure of a thyristor, it is basically having the 4 alternate PN layers. So here you can see that the layers involving the PN junction devices. So it is 4 alternate PN layers. And as a result, you will be having 3 junctions. So these junctions are J1, J2 and J3. The terminals are also 3, similar to other semiconductor device. Only difference is here you will be having the gate as extra in comparison to anode and cathode. So if we have seen the diode, in the diode we were having anode and cathode. So it was uncontrolled device. Now in order to control the diode, we are having one more terminal which is known as the gate. So if you see the symbol of this thyristor, it is having anode, cathode, and this is a diode symbol, and there is another terminal which is known as the gate. So this gate is the one which is going to control the VI characteristic of the thyristor and which make it to be more control device. So gate will provide the switching control and the junction areas will determine the ratings. So what rating we are basically going to use. If we talk about the operating principle, so the thyristor will be forward biased only when the anode voltage is greater than the cathode voltage, and the gate pulse will initiate the conduction process. There are internal regenerative feedback mechanism to make the self-sustaining conduction. So now the gate is one of the most important junction or the terminal which is responsible for this thyristor to turn on. And we need to forward bias the thyristor to get it turned on. So the key insight that we can take is there will be 3 PN junction which will create unique switching behavior. So this is the cross-sectional view of the thyristor having the P and PN layers, where the different terminals like anode, cathode and gate are shown, and different dimensions of the different layers, the PNPN layers, are also mentioned in the range of different micrometers. So it will be forming the different junction J1, J2 and J3, and these junctions will determine the rating of the particular thyristor. The thyristors are basically represented with two transistor equivalent model. So what is the two transistor equivalent model? This is a model of a thyristor when you are having two transistors T1 and T2. The T1 is in the form of PNPN, PNP, and T2 is in the form of NPN model. So this will create a regenerative feedback connection mechanism, and alpha 1 and alpha 2 being the current gain of the two transistors, you can have the loop gain condition when alpha 1 plus alpha 2 will be greater than equal to 1. So here you can see the two transistor equivalent model, the basic structure, where you have the transistor T1 which is in the form of PNP and transistor T2 which is in the form of NPN. These two are connected back to back to form two transistor equivalent body. So here you have the transistor Q1 and transistor Q2. Transistor Q1 is having the current gain alpha 1, transistor T2 is having the current gain alpha 2. So the current analysis says that the anode current IA is equal to alpha 2 into Ig divided by the 1 minus alpha 1 plus alpha 2. The derivation part I am not going here because we can see from the KVL and the KCL equation, we will be getting this relationship. Here you will be having some extra term which is basically because of the reverse leakage current, which is not of that important. So this is the most fundamental equation for the current of the two transistor equivalent model of the thyristor, which is the anode current. The critical insight that we can get from this equation is that the sum of alpha 1 plus alpha 2, if it is tending to 1, then the denominator will become 0, and as a result the current will be infinite, which can be thought of the turn on condition. So this operation sequence, if we talk about the two transistor model, so the gate current will increase the current gain of the transistor 2. The collector current in transistor 2 will become the base current of 1 because both are connected together for the transistor T1, and IC1 will be feeding back to transistor T2 base. So there will be regenerative action which will be sustaining the conduction process. Now we will see the transient behavior and what is dV by dt effect in case of the thyristor. The junction modeling, where you have any PN junction that can be represented by a resistance denoted by Rj and a capacitance Cj in parallel. So basically it is thought to be one resistor in parallel with one capacitor. So that is the formation of the PN junction. Now there may be two conditions, either it is forward biased or reverse biased. So in the forward bias condition, the resistor value will be equal to 0 and the capacitance will be negligible, or in the reverse bias condition, the resistor will be infinite and the capacitance will dominate. So this is what going to happen for the RC parallel network under the forward bias and the reverse bias condition. For the ACR transient analysis, the junction J1 and J3 will be forward biased, which will be acting as a short circuit or a closed switch. Junction J2 will be reverse biased, and this will be modeled by the capacitance, which is Cj2. So here you can see the dynamic model of a thyristor where you have the resistor and capacitor in parallel, and since you have three junction, so you have three resistor capacitor in parallel mode, and in the forward bias condition we will be acting as a short circuit, so the current will start flowing. So the current in the capacitor 2 or in the junction 2 will be equal to dq by dt. So this formula we can get it from the relationship of the current and the charge. So the Q can be written as C into V. So if you differentiate it, we can get the two terms where C dV by dt plus V CD by dt we will be getting. Now, since we can assume that the capacitance is constant, and as a result, we can think the current in the junction of the capacitor can be written as the formula C dV by dt, where the voltage is basically between the anode to cathode. So we can say that this relationship, the current is directly proportional to the ratio of dV by dt. So there is a concept of false triggering when if dV by dt is sufficiently high, then in that case the current will be increasing in the junction, and if this current is greater than the latching current of the thyristor, then the thyristor will turn on unintensely, which is not good. So it is known as the false triggering. So this dV by dt control has to be there, otherwise the thyristor will be turned on, which is not required. Thyristor operating states, whenever we think of, then there is basically three important operating states we will be discussing. One is the forward blocking state, reverse blocking state, and forward conducting state. So these are the three important operating states of any thyristor. Let us focus on the forward blocking state first, where the anode is positive and there is no gate signal. So we have not given any gate signal. So without a gate signal, the thyristor can be treated as the diode, and here the anode is basically positive. So there will be small leakage current which will be flowing in the microampere range, and the voltage will be limited by the breakover voltage. So the junction J2 will block the current flow. So there will be no current which is flowing in the forward blocking state. So the name has been given as blocking. In the reverse blocking state, where the anode is negative with respect to the cathode, there will be a small reverse leakage current, and this will be blocking up to the reverse rating. So the junction J1 and J3 will be reversed biased. So this is under the reverse condition. So reverse leakage current is going to fall. Now the main important state which we are interested in is in forward conducting state, where the gate triggered or the voltage breakover condition has achieved. So there will be low forward drop around 1 to 2 volt, and there will be high current capability of the device, and all junction will be forward biased. So we can say that the thyristor has become turned on. So this is under the forward conducting state. The key point is the state depends on voltage polarity, the current magnitude, and the gate signal. So three important things to be noted when we talk about the thyristor characteristic is what is the voltage polarity, what is the magnitude of the current, and what signal in the gate is applied or not. So here we can see the voltage current characteristic, where you have the anode to cathode voltage and the anode current. So you are basically having the three important characteristics: forward blocking, forward conduction, and reverse blocking. There is again one more which is known as negative resistance characteristic region. So thyristor VA characteristic, if you see, so here the gate is the one which is controlling the conduction. So as soon as you apply the gate current, and the magnitude of the gate current will turn on the thyristor. So we will be operating the thyristor here in the forward conduction mode. This is the reverse blocking mode, and there is a reverse leakage current which is flowing in the reverse polarity. So in the forward blocking, there will be low current until the breakover voltage, and this will be controlled by the gate current. Negative resistance is the unstable transition region, and there will be rapid current increase, which is not acceptable. Forward conduction is basically high current, low voltage, and it is limited by external circuit. And reverse blocking, where you have a small reverse current and there is avalanche breakdown because of the reverse breakdown voltage. So the design implications, if not done properly, then there can be a sharp switching transition. You have to take care of the hysteresis behavior as well as the gate which will be controlling the breakover voltage. So you need to control this design properly to have important BI characteristics. The critical note here is that the gate will lose its control once the thyristor will turn on. So if you have turned on the thyristor, there is no purpose of gate now. So the purpose of gate is only to turn on the thyristor. Once the thyristor is turned on, the gate will lose its control. So critical voltage parameters, we will be seeing some of the parameters in terms of the voltage. So the first one is basically DRM, which is known as the peak repetitive forward blocking voltage in the range of 400 volt to 12 kilovolt. You have RRN, which is peak repetitive reverse blocking voltage in the range of again 400 volt to 12 kilovolt. DSM, which is the non-repetitive forward blocking voltage, it is 1.1 times the VDRM. RSM is basically the reverse blocking voltage, which is non-repetitive. It is 1.1 times the VRM. TM is basically the peak on state voltage at rated current 1.5 volt to 3 volt, and BO stands for the breakover voltage when there is no gate signal. It should be greater than VDRM. So these voltages are taken care when we do the design of any thyristor. So the design safety, always take the safety factor 2 to 3 times, where you have the operating voltage should be less than VDRM by 2.5. So the practical note is always include adequate derating factor for temperature and aging effect, because these are not in our control, temperature as well as aging. So you need to have certain derating which is adequate so that external factor can be considered. So the selection criteria is choose rating 2 to 3 times the operating values. So whatever the operating values, around 2 to 3 times more, you have to keep it. Now we'll see the critical current parameters. So ITRMS is the RMS value on state current rating. It is 1 ampere to 6 kiloampere depending upon the thyristor. IT average is average on state current rating, which is 0.6 times the RMS value. TSM is peak surge current, 10 millisecond for duration. It is 10 times the average value. Holding current and latching current are the two important current in thyristor, which is the minimum to maintain on, that is the holding current. What is the minimum current required? Latching current is the minimum current after the gate removal. So this is in the range of milliampere. So IGT is basically the gate trigger current, which is 0.5 milliampere to 200 milliampere. So if you talk about the current, we will be focusing more important current in these three current, where you have triggered the gate signal using the gate current, and you need to maintain a minimum current to keep the thyristor on, which is known as the holding current. And if the gate is removed, then the current should not fall below the latching current. Otherwise, the thyristor will be turned off. So the critical relationship, which is reliable operation, where the latching current should be greater than the holding current. And the design rule is that the gate pulse width must ensure that the anode current is greater than the latching current before the gate removal. So whatever the signal you are giving, the pulse in the gate, its width must be ensuring that the anode current should be greater than the latching current when you remove the gate signal, because gate is required only to turn on the thyristor. You can remove the gate after the thyristor is turned on. Temperature effect is very important because all current will decrease with increasing temperature. So as the temperature will increase, the current will fall. So we need to include the temperature in our design current ratings. What are the turn-on methods? So there are different turn-on methods of a thyristor. You can have forward voltage triggering, gate triggering, temperature triggering, dV by dt triggering, or you can trigger using the light, which is the photon energy. So forward voltage triggering means the anode voltage is greater than the breakover voltage. The control is poor here and it is not recommended. Gate triggering is the one where the gate current is greater than the threshold limit. This is excellent and most common. So we will be going with the gate triggering in case of thyristor. Temperature triggering, where you have the high junction temperature, there is no control and you can have the failure mode. So it is not desirable. dV by dt triggering can be done with the false voltage, and it is a false triggering because there is a voltage rise. The photon energy can also trigger, which is good and can be used for special applications. So what is most common? The most common is basically the gate triggering, where we have to focus on. So the preferred method that we will be going is in the gate triggering. Some of the advantages are it has the precise timing control, low power requirement, reliable and repeatable, and the fast response time. And the typical requirement that you need for the gate signal is having the gate voltage 1 to 3 volt. The gate current has to be 10 to 200 milliampere. The pulse width of the gate signal should be greater than 1 microsecond and the rise time should be less than 1 microsecond. So whenever we are giving the gate pulse, this condition has to be met for proper turn on of the device. Now let us see the turn on process mechanism. So we saw that it is the gate whose signal is going to turn on the thyristor. So what is basically this turn on mechanism? So a thyristor is going to be turned on only when the forward biasing and the gate pulse, which is positive, is applied. So two important conditions need to be met. First, the forward biasing has to be there and you are going to apply the gate pulse which is positive. Then only the thyristor is going to be turned on. Thyristor transition from forward off state to on state takes certain finite time and that is known as the turn on time. This turn on time is basically the summation of three important time which is known as the delay time TD, rise time TR and the spread time TP. Here you can see the turn on characteristic of a thyristor. So you can see the turn on time, total turn on time T on is basically the summation of certain delay. Then you have the rise time and then you have the spread time. So this delay is where you have from 0 to 10% of the anode current. Then from 10% to 90% you will be getting the rise time. Then the current is going to be settled, which is the spread time. Then the thyristor is going to be turned on and the gate current is applied and you will be having certain anode voltage. If you talk about the detailed analysis of this turn on, so what is the delay time? Delay time is when the gate signal is applied to 10% of the final anode current. Here the anode cathode voltage will drop from 0.9 times the VD value to 0.1 times the VD. And this is the initial response phase. Typically this time takes 0.1 to 1 microsecond. This is the shortest phase during the turn on process. When we talk about the rise time, this is the anode current which rises from 10% to 90% and the anode voltage will continue dropping. There will be strong dependence on the gate drive current and typically this current is in the range of 0.5 to 2 microsecond, the rise time. So here you can see this is about, we can think to be around 2 to 5 times. Here the circuit will be influenced because of the RL circuit nature if you have the slower rise, and it is RC circuit which will give you the faster rise. So rise time, after that you will be having the spread time where the voltage will drop to the final on state value, current will reach the steady state and the conduction will spread across the cathode area. This is the longest duration, around 1 to 3 microsecond. The physical process here, the current will be spreading laterally from the gate region. So complete turn on sequence, if you understand, you are applying a gate response which is given by the delay. Then you have the current build-up, which is the rise time, and full conduction is basically the spread time. So turn on time is a summation of delay, rise and the spread, which is typically 1.6 to 6 microsecond duration. Gate triggering design, if we talk about, then the essential requirement is the gate signal must be removed immediately after the turn on process. So you need to remove the gate signal. No gate signal when thyristor is reverse bias. So if the thyristor is reverse bias, then there is no impact of this gate signal. Gate pulse width must ensure anode current reaches the firing current and the gate current amplitude should be 3 to 5 times the minimum triggering current required. Higher gate current will reduce the turn on time. So if you want to on the thyristor with a fast due time or duration, you need to give more current. So the design equation that you need to follow is the gate current should be greater than 3 to 5 times the threshold value of IGT. And the pulse should be greater than the on time plus certain safety we need to account duration for circuit variation and temperature effect to be taken into consideration. Temperature is one of the most important factor because the gate triggering requirement will depend upon the temperature and the design for worst case condition you need to take into consider this temperature into account. The turn-off process is basically known as the commutation. In the next lecture 6b, where we are going to discuss more detail on the thyristor commutation circuits and its process, here we are going to see the overview. So thyristor is basically turned off when the anode current will fall below the holding current. So if the anode current falls below the holding current, thyristor will be turned off, and this process is known as commutation. There are two important commutation methods. One is the natural commutation and another is the forced commutation. Turn off time is basically the time from anode current becoming zero until the SCR remains or regains its forward blocking capability. Mathematically, if we say the turn off time is the summation of two important times. One is the reverse recovery time TRR and another is the gate recovery time TGR. So here you can see the characteristic of the anode current. So this time PQ, which is the off time we can say, which is the summation of TRR plus TGR. So first the anode current will fall, then regain back, and then it will be settling down. So this is because of the different charges of the reverse recovery and recombination process taking place in the VI characteristic, due to which you cannot turn off the thyristor instantly. You need certain duration and certain external circuit that will be commutating the thyristor. If we talk about the detail for the reverse recovery time, this is the physical process we talk about. Then in the previous graph, at time t equal to t1, the anode current will become 0 and this will be initiating the turn-off process. The reverse recovery current will flow due to the stored charge in the carrier. And from the duration t1 to t2, the carrier will be sweeping up from the junction J1 and J2. And t2 time, 60% of the stored carrier will be removed and reverse current magnitude will reduce. So the design consideration that you need to take care is rapid decay can induce reverse surge voltage. It need to be mitigated using special circuit which is known as the RC snubber circuit. Recovery charge relationship, if we see, which is QRR, is basically the product of IRR and TRR. QRR is the reverse recovery charge, IRR is the peak reverse recovery current, and TRR is basically the reverse recovery time. Typically, this time is in the range of 5 to 30 microseconds. That depends on the device construction and the operating conditions. The next time, which is known as the gate recovery time, this is the final recovery phase, and at time T2, the reverse recovery current approaches 0. Thyristor can now block the reverse voltage. However, the junction J3 is still containing certain stored charge carriers, so it will be preventing the effective forward voltage blocking capability. So what is the recovery process then? The reverse voltage must be applied to remove remaining charges present in junction J3. So you need to apply certain reverse voltage. The charge removal occurs through recombination process in the duration T3 to T4. The gate recovery time represents the time for complete charge recombination, and at time T4, the thyristor will be fully turned off and can block the forward voltage. So TGR is basically the time for junction J3 to clear off all the stored charges. Critical design point, the thyristor cannot reliably block the forward voltage until TGR is complete. So TGR you have to complete, which is the charge recombination time. All the charges in the junction J3 will be removed, and this typical range of time is 10 to 50 microseconds. And again, it varies with the type of the device as well as the temperature. Now we will see the gate characteristic and safe operating area. So the gate behavior, if we talk about, the SCR is triggered by the positive gate voltage or the gate current. The gate characteristic will vary depending upon the manufacturing tolerance. Gate cathode junction will behave like a standard PN junction diode. So this is the gate behavior. Some of the critical gate parameters that we will see is what is the minimum gate current for reliable triggering, that is IG minimum. What is the minimum gate voltage for reliable triggering, that is VG minimum. Non-triggering gate voltage, its maximum safe level, that is VGNT. IG max and VG max are basically the maximum allowable gate parameters in terms of current and voltage, and the average power which is dissipated is given by PG. So the power constraint is the product of VG into IG should be less than the maximum power PG max. Design guidelines: operate within safe operating area for the gate characteristic. So this we are going to see the gate characteristic, and you have to operate it within the shaded safe area. You have to maintain the noise immunity. Signals below BGNT will be the threshold limit. Account for temperature variation and component tolerance. So this we need to taken into consideration. So the gate drive circuit, let us see. So this is the basic triggering circuit configuration. So here you have the thyristor. This is the anode, cathode, and the gate is connected to the trigger circuit. Anode is connected to the supply through the load resistor. So Vs is basically the gate source voltage, which is the DC supply, and Rs is the limiting resistance. Vg is basically the gate cathode voltage drop, and there is a gate current through the circuit. So if you apply the Kirchhoff's voltage law, the Vs is equal to Ig into Rs plus the Vg. Vg is here across the triggering circuit. And the load line equation, if you do it in terms of this equation rearranging, we'll get the gate current is equal to Vs minus Vg by Rs. So load line analysis if we do, then the load line will intersect the gate characteristic at the operating point Q, which is the quiescent point. Varying the resistance will change the slope and operating point. Operating point should lie between the minimum maximum characteristic. Load line we have discussed very detailed in one of the lectures, and how the load line is basically calculated. You can go through that lecture and see it. So the pulse triggering and power management. Pulse triggering is having certain advantage. So when you increase the gate current, it will significantly reduce the turn on time, and it is the pulse width which must be greater than the on time of the thyristor for reliable triggering. It allows for higher instantaneous power for short duration. Power relationship, if you see the maximum instantaneous gate power PG max is basically 2 times the PG average by the total pulse width T. Frequency power relationship, so frequency is inverse of this pulse width. So I can say that the T can be substituted as the twice of the frequency. Now here, if you can see that the gate current represented by the pulse width, so you can have high frequency pulse waveform. So here you can see lot of pulses are there for the same time period, which is high frequency pulses. This is short frequency pulses. So design constraint that you need to maintain is that always ensure that the product of Vg into Ig should be less than Pg max with adequate safety margins. Now we will see the gate power dissipation example, one of the example we will be taking. Let us see and understand that if the Pg average is 0.45 watt, which is the average gate power limit, and for different gate voltage level, let us take an example of 2.5, 5, 7.5 and 110 volt. The gate current is the ratio of the average volt power by voltage. So for these voltages, you can find the different current of the gate or the different voltage of the gate levels, and you can draw the curve between the gate voltage and the gate current, which is known as the gate characteristic. This will be showing the power dissipation curve. So this curve, what you need to take care is that, so this is basically the load line what need to be designed, and this is your operating point, which is the quiescent point, which is cutting one of the gate curve number 3 at this point, which is the Q point operation. Key insight is that the power hyperbola limits allowable operating combinations of Vg and Ig. So the safe operating area is this one where you need to operate the thyristor. So this will be the operating area of the thyristor. The two important protection that we need to take care is basically the di by dt protection and dv by dt protection. So di by dt protection, what is the problem is with that you have the fast current rise which will be creating the hot spots. These hot spots result in localized heating and it will be damaging the device. The currents spreading will take certain finite time. So the rate of change in the current di by dt result in the formation of hot spot, and this hotspot will be damaging the device, and this will always taking certain finite time. What is the solution to take and protect this? The solution is to have the series inductance incorporation, because we know that di by dt for the circuit having the inductor is basically Vs by Ls. So Ls, which include the stray inductance, and the design rule says that Ls value that need to be incorporated is basically equal to Vs by the maximum value that comes for the di by dt. On the other hand, the dv by dt protection, which is we have seen that as the dv by dt increases, it causes the false triggering. So the capacitive displacement current will result in unwanted turn-on condition. What is the solution here then? One circuit which is known as the RC snubber circuit we can incorporate to protect this dv by dt. So dv by dt here will be coming 0.632 Vs by the time constant, which is the product of R and C. So the design rule, we get it. What is the product of R and C? Will be rearranging this equation to form 0.632 Vs by dv by dt max. So this is the combined protection circuit where you have the inductor connected in series with the thyristor, and you have a RC network which is forming the snubber circuit with the help of one diode. So both protection is very important, and let us see in detail about the snubber circuit design. So basically the thyristor, which is forming due to the 3 PN junction with specific biasing, here the forward bias condition J1 and J3 are basically forward biased and J2 is reverse biased, which is leading to capacitive formation. And if there is a high dv by dt in the range of 20 to 500 volt per microsecond, this will cause unintended turn-on condition for the thyristor, and the solution lies in the snubber circuit because it will be limiting the dv by dt and protect against this transient. Snubber circuit, which is basically the series RC circuit which is connected in parallel to the thyristor, where the capacitor will limit the dv by dt across the thyristor and the resistor will control the capacitor discharge current. The switch closing, if you see it here, there is a switch which is connected, the RC snubber circuit which is connected in parallel with the thyristor. So if the switch is closed, the capacitor will charge and keep the thyristor voltage low. The gate triggering, the capacitor will discharge through the thyristor and the current will be limited by the resistor. So snubber circuit configuration is shown here, which is avoiding the false triggering of the thyristor. Circuit analysis, if you do, then the voltage Vs can be written as the sum of the two factors, one coming from the resistor and another coming from the inductor, and the current I of t can be obtained from the solution of the differential equation, and here under zero condition for time you will be getting Vs by L. So this design equation, if you see, the maximum current rate di by dt maximum is equal to Vs by L, and snubber parameters where the resistor will be depending upon zeta being the damping factor 0.5 to 1 and under root of L by C. So the capacitance value can be obtained from this damping factor and dv by dt maximum condition with the inductor. Let us take one design example to understand. So if the peak voltage is 200 root 2 and the peak current is 100 ampere, then dv by dt maximum being 400 volt per microsecond, di by dt maximum 80 ampere per second, the safety factor will be 2 and the minimum resistance required will be 20 ohms. Design consideration, you include the safety factor and account for component tolerance in the final design. Some of the major application and the market segment, if you see, then the thyristors are basically used in power conversion systems, in AC to DC rectifiers, AC controllers, DC choppers, cycloconverters and static switches. So these are the conversion devices. In high power application systems, in HVDC, high voltage DC transmission system, or FAT devices, which is flexible AC transmission system, wind turbine converter, electric arc furnaces and electrochemical processes. Thyristors are also used in industrial applications, in motor speed control drives, electric furnace control, welding, power supplies, UPS system and battery charges. Selection criteria of these thyristors are the power rating should be greater than 10 kilowatt, switching frequency less than 1 kilohertz. They are very cost sensitive applications, high reliability requirement and harsh operating environment also we can use it. So market is dominant of high power and low frequency applications. So we need thyristors which can be of high power and low frequency, then those are suitable for the market position. Let us do the comparison for different power semiconductor devices. We have already covered the BJT, MOSFET, IGBT. Now here we will be seeing the thyristor comparison in terms of different parameters, the voltage, current, switching frequency, gate turn-off, on-state loss, drive complexity, the cost. So the thyristors are basically used for voltage greater than 10 kilovolt. So in this range you can see it is the highest. Current rating also greater than 5 kiloampere. So again it is the highest among other power semiconductor devices. Switching frequency less than 1 kilohertz. The gate turned off is no here in thyristor, but yes in all the other power semiconductor devices. So you are requiring the commutation circuit. On-state losses is the lowest in case of thyristor as compared to the other power semiconductor devices. It is also low in terms of drive complexity and cost. If you take, then in relative, if you can take, then this is also the lowest. Device selection guidelines, if you take for the choose thyristors, then they are basically used for high power, low frequency, cost sensitive applications, high reliability requirements, simple control schemes, and avoid thyristors in the condition of high frequency switching, frequent on-off control, low power application, complex PWM control and fast dynamic response. There you do not use the thyristors. Now we are going to use the thyristor in two important modes. One is the series operation where you need the voltage sharing. Here the thyristors will be connected in series so that the voltage can be shared between different meshes. So the design challenge is the device characteristic may vary due to the manufacturing tolerance and there may be unequal voltage sharing which can cause the catastrophic device failure. The temperature also play an important role because it significantly affects the leakage current and dynamic voltage sharing during the switching transit. So the design equation is the voltage across the thyristor 1 is depending upon the number of such thyristors which is connected NS and delta ID is being the leakage current here. So we can compute the voltage across series combination of the thyristors using this equation. Resistive voltage sharing solution, equal resistors across each thyristor force voltage distribution. So we need to use equal resistors when we need to connect it. This resistor can be designed as depending upon what is the rated voltage and what is the leakage current. So we need 10 times of the leakage current. Continuous power dissipation trade-off will be taken and additional RC snubbers will be there for dynamic sharing. On the other hand, if you need current sharing, you can go with the parallel operation where the thyristors are connected in parallel. And this is the series resistance mode, parallel operation. And you have the magnetic coupling mode also where thyristors are connected in parallel and inductors are magnetically coupled. So let us see the difference between resistance, current sharing and magnetically coupled method, two important methods for parallel operation. If you go with the resistive current sharing, then this is simple and reliable implementation. It is excellent current sharing accuracy, continuous conduction power loss will be there and resistance RS depend upon the difference of the voltage on condition and the rated current and there will be power loss which is I square R. If you go with the magnetic coupling method, this is significantly lower conduction losses will be there, automatic current balancing mechanism, fast response to current imbalances, more complex because the magnetically coupled circuits are there and higher initial cost investment. So if the circuit needs simple construction, then you go with the series resistance method. But if you require the conduction losses to be low, then go with the magnetic coupling method. Critical requirement will be you need a heat sink which is common for thermal stability. You need match device characteristic preferred and synchronized gate drive signals. Then only the thyristors will be turned on or turned off easily. Now, what is the modern thyristor variants and what are the emerging technologies? If you talk about the enhanced control devices, so there is another family of thyristors which is GTO, gate turn off thyristors. This can be controllable for the gate to be turned off MCTs are basically the MOS controlled metal oxide semiconductor field effect based drives, and IGCTs are integrated gate commuted, which is high power switching. There is emitter turn off thyristors also, which are advanced control features. If we talk about the performance enhancement, we require faster turn off time, higher dV by dt immunity, integrated protection features, improved thermal performance, and lower on-state voltage drop. So these will enhance the thyristor performance. Some of the specialized applications are in the form of TRIAC, RCT, LTT, BCT. These are the specialized applications of the thyristor groups. TRIAC stands for bidirectional AC control device. You have reverse conducting thyristor, light activated thyristor, or bidirectional control thyristors. The future technology trend lies in silicon controlled thyristors, which are high temperature operation. You can have smart power modules, integrated control electronics, wide band gap semiconductor devices for enhanced performance characteristic. And AI plays a very important role now to have the enhanced control in predictive switching algorithm. So what is the evolution? So ACR came at 1957, then we moved to GTO in 1980, 2000, we moved to IGCT, and now the feature lies in silicon controlled rectifiers. Now we will summarize what we have discussed and what is the key takeaways. So the fundamental characteristic, thyristors are basically PNPN structure, which is having a regenerative switching mechanism. Gate triggering provides the precise timing control. Latching behavior enables self-sustaining conduction, and high power capability make it industry standard. So these are the most important characteristic of the thyristor to be taken into consideration in the industry. And the performance parameters, voltage up to 12 kV, current up to 6 kiloampere, turn on time 1 to 6 microsecond, and turn off time 50 to 80 microsecond. These are standard typical performance parameters of the thyristors. We need to control the thyristors in terms of protection, dV by dt protection, di by dt protection effect. Thermal management is absolutely critical. There are series parallel operation which need to be carefully designed, and gate drive circuit reliability is essential. Application, we are using the thyristors in wide application in terms of power conversion, industrial motor, drives, HVDC transmission system, and electric furnace control. So this complete the discussion on the lecture on thyristors, the basic principle and characteristic. Next lecture we have the discussion more on thyristor commutation techniques. How do we turn off the thyristors? What are the special circuits, and how the natural commutation is different from the forced commutation. So we have covered all the power semiconductor devices by now. The special categories of these thyristor families, which are the advanced thyristor families, we will be taking into consideration in the coming lectures. Thank you for now.